Hello, my name is Bernat Espigolet, and today I'm going to be talking about the history of mathematics project, and especially the 8 learning journeys that I've been creating for the past year. So let's start. The history of mathematics project is a website where we exhibit 74 artifacts pages in 9 different exhibits, and additionally we added 8 learning journeys that connect different artifacts, and we explain a fun story just by picking some of these interconnected and related artifacts from the past. So we have the homepage. This is a history of mathematics with surrounded by istash.org, and then we have these 9 virtual exhibits in this section there, and which contain 74 artifact pages. And then we have this last part with 8 learning journeys. Today I'm just going to be sampling 2 of those. And so the Wolfram group, the team it was quite small, but we created this website in a short amount of time. And then we also consulted for the content. We have the contributions from 50 domain experts in relevant areas of the history of mathematics. So it spans from prehistoric to more recent mathematics, and you're going to see some of the examples that we have there. So that's the 2 main sections there. Each interactive exhibit so we have 9 interactive exhibits where we are classifying these 74 artifacts that I mentioned. And for example, if we take the counting exhibit, you're going to find that you have a navigation to the other exhibits when you click this bar in orange. Then we have a short description about the exhibit, a clickable timeline where you can find the actual timeline when these artifacts were developed and see the related ones. And actually, when you click one of those thumbnails, then you get to the artifact page. For example, that's the case for the Inca Pana. That's a kind of an abacus from the South America. And you see that in this artifact page, you also have the browser exhibit to the other exhibits and different sections. And then we have a short description, a hero image with a more detailed description of the artifact. And then you have several thumbnails that you can click, and it's a carousel, and you can see different examples of that particular artifact. Then we have the metadata. So that's, for example, showing the dimensions, locations, the catalog number, where it's, and the current location where this artifact is found right now. And then you have the interactive timeline that you can click to related artifacts and see where it falls. And then the 2 other parts of the page is divided by the interactive content. That's more a short overview of what's about, and you're going to actually use the manipulate to explore and have a first impression about the artifact. In this case, you were using, for example, bins, and then with really simple rules, you end up with the ending state, and that's your sum. And you can do that quite basically, but here is just a simple interactive example. And then the main part is the computational explanation, and here it's more in depth, and it's a step by step using the Wolfram language, and you can find how it works and why it was designed this way, this artifact. Finally, you have the other resources to related artifacts. In this case, it's South American quipu, which is related, and the Incas were using it to register and store large amounts of numbers. And so the computation was done in the Inca Pana, and then you had the South American quipu to register all this data. And then the additional reading is the other section that you have, where you can find the bibliography, and you have more like articles, books that are relevant to the artifact that we are like presenting. And finally, the additional links, you can find videos, other websites that are related, and it can help you like understand more and create activities for that. So that's the structure for the exhibits and the artifacts. But then we found that because some of the artifacts are related to each other, for example, we have counting and arithmetic, both with the Kipu and the Yupana, but we can explain a story, and that's what we did. We created stories for several artifacts, and that's what we get when we present it in a nice, fun way for kids to explore. And that's this case for the mathematical beans and notated strings, where it also presents the ideas across cultures and time, because we present more ancient civilizations like the Mochi culture that was in Peru at that time, but we can find some connections between the different cultures in South America. So the learning journeys are intended as a fun journey through the mathematical artifacts, and it's aimed at the students interested in the mathematical story. And it's also useful for classroom explorations. And it contains images and links to individual artifacts, and includes interactive content. And it's primarily visual, as you will see. I'm going to be giving an overview of these two learning journeys. And I have to say that behind these original journeys, there is a lot of reading involved, and here is some of the books I read, and that's my favorite ones, because they influenced me how to understand this history of mathematics from a different perspective. And you can see, for example, Ancient Games of Chance. It's one of the stories I picked because I was, for example, in the polyhedrous virtual exhibit, we have several dice. And when we try to understand how they emerge in the periods of time, we can find some interesting connections about them. And there is like two of them are icosahedral dice with 20 faces, so you can cast that dice. And these dice were usually made for casting and trying to predict the future. They were like found in temples in Greece and also in Egypt. But one of the dice that interested me the most was this one from the burned city in ancient Iran. And this device was this game board was found in the burned city in the graveyard. And there was an Italian expedition that went there in the 70s, and they found there this game board that's called a 20 squares game. That's a game that was played in this area, but also in the Indus Valley and in ancient Mesopotamia, in ancient Iraq. So these elongated dice, they had marks only in the 4 rectangular faces. So you could cast any number from 1 to 4, and you can see that probably from that elongated dice, they eventually evolved to the 6-sided dice that we are still playing today with. And so that game board was a racing game, so you had 2 players, and they had to scroll and go through all these different pathways until they escaped. But they had like 5 tokens, and they had to use them. Here is the same example, but from the city of Ur in Mesopotamia. They've also found these game boards that were played in there. But here you can see that the dice that they were using were tetrahedral shaped, instead of like these rectangular dice. And also in actually the rules of the 20 squares games were recovered from a tablet. It was deciphered by Irving. Irving Finkel at the British Museum, they actually deciphered it quite recently, and now it can be played again, but it was lost at some point. And we can see that the culture was spreading, and all these games were spread across different cultures, because we can find the same kind of arrangement. That's the 20 square game for the Egyptians. Instead of having these two, well, it's just like a straight line, but you can count it's going to be also 20 square games. And here the randomizing device were the chip knuckle bones that they were like throwing it, and you can cast different values from the different sides of that bone from the chip. So that's probably where the six-sided dice evolved from, and it was very popular from the Greek period and also the Roman period, and up to the Middle Ages. For example, we have this interesting book from Alfonso X of Castile, that they compiled all the known games about dice, and also for tables, because this 20 square game was a predecessor of the backgammon. Backgammon is the modern version of that, but it was related. And so from that book, it's interesting because you can actually reconstruct and see all these games, how they were played. They usually involve throwing three dice. So you roll the 3 dice and you get some results. And actually, I made a demo for them in using the Wolfram language. Let's see it. It's this little code there that here, for example, for a third, the first to roll 15, 16, 17, or 18, or the opposite values, so 6, 5, 4, or 3, is the player who wins. So you just play, and then you can find different values. That's not right. So you keep rolling until some of the players get that numbers that you're looking for. So in this case, player 2 wins, but there is other types of games involving 3 dice. And from the history perspective, you can see that at some point they were quite popular. And actually, you can find in some cities that they were banned for several periods of time. And it was kind of like the casino experience from the Middle Ages, but it spread until the Renaissance. And so, for example, what I try to do with this learning journey is to show that from this evolution of dice, you end up with the emerging with the beginnings of the mathematical theory of probability. For example, with casting using 2 dice, the sum, you can get all these values, and the most probable, the probability that's more frequent is the number 7. That's with all these combinations, you get 7. So that's the advantage number. And if you use 3 dice, then the 2 numbers that are more probable, it's going to be 10 and 11. So that's was not really known as. So Galileo was one of the ones who published a paper showing that. So he stated that with 3 dice, you can only be one way to obtain, for example, 3, and then also you have 18. So that's only one way. So, but he enumerated all the possibilities for the half of that, and he argued that there is a symmetry. So you get all these other values that are the same chance of that. And from here, you can see actually that's approaching a normal distribution. And actually this kind of visualization, it's very easy to do with the Wolfram language, but you can also assemble a group of people like a classroom and draw all the possibilities. And actually you can understand a little bit of how it works, and that was the motivation when mathematical theory started. It started because they wanted to analyze games that were very popular back then. So that's one of the journeys. And yeah, if you click, if you go through it, you're gonna see that, for example, you can find the actual letter from Galileo, who was analyzing this problem. And here you see for half of the diagram, he actually enumerated all the possibilities in there. So now let's move to the other learning journey that I'm going to be showing, and that's for the weighting system used in Mesopotamia. So the barley grains were very important, and actually they were so important that they used as the smallest unit of length, area, and volume and weight. So they had the whole system to be based on the grains of barley grains, and from that you're going to see that, for example, you had that 180 barley grains was known to them as a shekel. So that word that is still used, and the shekel was to weigh out, but one shekel stone for example, a shekel of silver weighted 180 barley grains. That's about 8.4 grams. But the thing is that 60 shekels weighted 1 mina, and then also 60 mina weighted 1 talent. And that's when you get this this number system based on 60. And it was quite interesting because you can divide that number by in different ways. So for example, it can be divided by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. And so that was quite useful in the sense that you could do arithmetically easily, and they knew how to do and share things between different groups of people. These weights that have been recovered, there are many from different cities of Mesopotamia. For example, that's most of them were shaped like barley grains, but some of them were also shaped as duck shaped. That was quite frequent as well. And there are examples of other more exotic shapes, like this grasshopper and even frogs that were used. And in Egypt, they were using a different system, not base 60, but they were very careful about measuring precious things like gold or other stuff. So I have to mention that all the interactive content here, you can go and click this button here, and you can see that you can make your own copy or even download the code. And if you do, then you can actually see what's in this manipulate. And if you double click, for example, this site, and you're going to see the code, and from that you can explore yourself using this slider and see that different number of grains are computed by using different weights. In this case, duck-shaped weights. So, yeah, it's kind of nice to see how easy it is to find the actual values. So here the beam of the scale is acting as the inequality when you have the balance and you have the right solution for that, and it's kind of like one of the more prehistoric ancient mathematical artifacts that I can think of. So I'm gonna be stopping here, and so thank you for your attention. And now if you have any questions, I'm gonna be glad to ask, to answer that. And I have to be thankful about the team group and also all the people who were involved in the project. and especially Momath, Wolfram, and the Overdeck Family Foundation. Right. And so yeah, one last part is that using the Wolfram language, it was easy to create all the relevant data. So you had all these text, images, metadata, mathematical content, and interactive content in a single place using notebooks. And then from the notebooks, you create the website, and then you can update that simply by checking for changing notebooks, changing the notebook contents, and you get the final website. So that's a good way, and you can also provide and compute the timelines and have all your system in one environment. So let me check. I'm gonna stop sharing my screen and see if you have any questions. So that you have the right links there. So thank you, Andrea, for sharing that. And I have there is a question there from Brita, if there is a way to download the notebook component from the page. For example, in this case, if we share the screen again. So the answer is yes. There is a way to get access to the content, and so for example here, if you go to this artifact, for example, you can see that there is this part of the content, and from here you can actually download the content. And for the computational exploration, you have the same. You have the whole section that can be downloaded. And so, well, here I'm just going to use the file. And from that, you can see that it's going to actually work in your desktop using Mathematica. And here it is, the whole computational content there, and you can export it in your desktop version of Mathematica. But it's actually working also in the cloud. So for example, if you take any of those, you're gonna see that's interactive using Chrome. So let me see if there is another question. It seems that there is not. So thank you again for your attention. And we're going to be having several live streamings in the upcoming month. Yeah, so let me, yeah, that's all for now. And yesterday it was published, this blog post I wrote, and there at the last part you can find the actual dates for the upcoming events. October 25 and also November 22nd. It's going to be hosted by Momath, but that one is going to be with Stephen Wolfram and Eric. So that's going to be interesting to see. And so I'm going to be there as well. So thank you for your attention.